Thank you very much for having me. My name is Xiaosong Wu. I go by Andy. I'm a postdoc research fellow at the University of Melbourne. And this is a joint work with Matt Lewis at Clemson University and Frank Wolak at Stanford University. If raises. Oh, here we go.
Yeah, now
all right. Thank you. All right. So since Stigler 1961, consumer search models have shaped how economists think about consumer behaviors and market competitions in many markets. And in search models, search is characterized as a trade-off between the benefit of search and the cost of search. And there's a large empirical literature that structurally identifies search cost in many markets based on key assumption. And this key assumption is consumers know the price distribution. This is a convenient assumption because it allows econometricians to derive the benefit of search directly from the empirical price distribution, but we know it is a very strong assumption. First, it assumes that consumers have a correct initial price belief, meaning that their price belief aligns with the true price distribution. And second, it assumes that consumers do not update their beliefs as they receive new information, meaning that consumers are perfectly confident about their beliefs and they do not learn. And we know that in many markets, consumers are unlikely to know the price distribution with any certainty. For example, if consumers are unfamiliar with the market, or if the market conditions are changing rapidly so that the price distribution fluctuates significantly over time, so it is unlikely that consumers know the price distribution here. And by eliciting consumers' price beliefs, experimental papers have found that consumers tend to have prior beliefs that are different from the actual price distribution, and they update their beliefs as they receive new information. So this is consistent with price distribution uncertainty and learning. And also Collier 2013 and De Los Santos et al. 2017 finds that if significant learning is occurring, ignore learning can generate biased search cost estimates. And this can lead to incorrect counterfactual and welfare analysis. And perhaps most importantly, so if we ignore learning, we may have incomplete understanding of market outcomes because learning affects the benefit of search, and together with cost of search, they influence consumer behavior and market outcomes. So more specifically, Lewis 2011 finds a reduced form evidence that the observed price patterns in the retail gasoline market are consistent with a model where consumers have price beliefs that are different from the actual price distribution. And these price patterns cannot be explained by search cost alone. So here we see that incorporating consumers' price beliefs and learning is very important. So in this paper, we asked the following question: can we identify consumers' price beliefs using just price and quantity data in the retail gasoline market? Can we identify if consumers know about the price distribution or they don't know it and they formulate their prior beliefs about the price distribution using the prices they observed from the past, likely from their most recent gas purchase? And do consumers update their beliefs as they observe new information, and how fast do they learn? All right, so before I get to it, so John Asker said in the APLC meeting last week that every good structural paper needs to have a good picture, and this is our picture. So this figure plots the average price level and the wholesale cost in the sample market. So the horizontal axis shows you the sample period. The blue line shows you the average retail gasoline price level in the city. And the orange line plots the spot price, and we use it as a measure of wholesale cost. So first of all, we can see that price level fluctuates significantly over time in response to volatile wholesale cost, right? So it is unlikely that consumers know the price distribution. And secondly, we can see that prices, well, prices. Oh, good call. Yeah, we see that prices tend to increase faster than they fall, right? So one explanation is that when consumers are uncertain about the price distribution, they're likely to formulate their prior beliefs based on past prices. So when prices are increasing, so the newly observed prices are likely to be higher than consumers' expectation. So consumers will search more, and as they search more, competition intensity in the market increases, profit margin shrinks, and cost pushes up prices very fast. Whereas when prices are decreasing, the newly observed prices are likely to be lower than consumers' expectation, and they will search less, and competition intensity in the market decreases, profit margin increases, and prices fall down slowly as cost goes down. So here we can see that variation in consumers' price beliefs generate asymmetric search behavior, and that generate asymmetric cost pass-through as a market outcome. So in this paper, we relax the known price distribution assumption, and we estimate a search with learning model that builds on Rothschild 1974, and we apply it in the retail gasoline market. So our learning process has two components. So first, so consumers are now to formulate prior beliefs based on past observed prices, and then consumers are now to update their beliefs as they, search along their driving trip. They update their price beliefs before they make a decision at which station they want to stop and purchase gas. So this is essentially an application of an optimal stopping problem. And we estimate the parameters governing the search and learning process using a novel panel data set of station-specific prices and quantities, and we combine it with data that describe the traffic flows in the city. All right, so ideally, identification of learning requires observation of individual search histories, because now consumer search behavior is influenced by their posterior beliefs, which is a function of all the prices that they observed prior to purchase. Right, so when individual search histories are not observed, integration of all unobserved search sequences can quickly cause the curse of dimensionality problem. And we overcome this challenge in this paper by leveraging a crucial observation in the retail gasoline market. So price search in this market is not random, but ordered. So consumers observe prices in the order that they encounter each station along their driving trip. Right, so here the assumption is the search order is exogenous to consumers' search process. Right, so here consumers do not deviate from their predetermined travel route in search for lower gasoline prices. They just search along their predetermined travel route. So you can think of it as a special case for Wetzman's sequential search model, where the deviation cost is infinite. Right. So based on this assumption, we can use the traffic data to simulate this empirical distribution of search sequences. And then the total gasoline sales at each station is just an aggregation of consumers' purchase decisions as they search and learning along their specific driving trips. And so here, right, as prices fluctuates over time, we know how this fixed order of prices affect consumers' posterior belief and how that affect consumers' purchase decision. And then the joint variation of the sequence of prices and market shares identify learning. All right, so preview of the result. So we find that learning is a crucial component of price search in the retail gasoline market. And consumers place a significant weight on past prices when they formulate their prior beliefs. And this results in consumers' prior beliefs to be different from the actual price distribution. The average absolute difference between consumers' price belief and the actual price level is 2.7 cents per gallon. And consumers are uncertain about their price beliefs, and they learn very quickly. So few new price observations can quickly shrink the initial difference by a large amount. So one new price observation can reduce the prior bias by 77%, and two new price observations can reduce the prior bias by 87%. So by the way, when I say prior bias, you may not like this terminology, but when I say prior bias, I more specifically mean how different consumers' prior beliefs are from the actual price distribution. Right, so we also find that order search can generate more realistic substitution patterns across stations. That depends on the amount of shared traffic. And we also generate demand elasticities that can change over time with fluctuations in consumers' price beliefs. And this is consistent with the rocket and feathers phenomenon that we saw in the previous graph. And also we find that learning can generate negative cross-price elasticities for certain station pairs. So this is an interesting result, and I'll talk more about it later. All right, so any questions so far? Yeah.
Is there anything in the data that tells you that search is ordered, or is that just intuition?
So this is just an assumption. Yeah. And well, later we'll show that there are actually plenty of stations along each travel route. So yeah, so there are plenty of options for consumers.
On any route where you see lots of people going one direction, the price gradient should be very clear.
Right.
I think it implies some interesting things.
Yes, but a station is located like on multiple routes and with multiple search orders. So yeah, so it's kind of hard. And also we only have, like, as you can see, we only have 46 stations. So if we compare it across stations, it's hard to get significant result. Yeah. All right, so data. So the market is a mid-sized city in the United States, and the market, the sample period spans from December 2014 to May 2016. So we web scraped daily gasoline prices for all of the 46 gas stations in the city, and we obtained daily total gasoline transactions for 33 of the 46 stations from a major credit card company. And we also observed the empirical distribution of traffic flows. So we get this data from the origin and destination table from the Department of Transportation. So this OD table basically divides the city and its surrounding area into many small traffic zones. And we know the number of drivers driving from one traffic zone to the other traffic zone. And for each traffic zone pair, we can find a single fastest travel route along the street network that connects these two traffic zones. And then we can find the stations that a travel route goes past. So for example, this travel route goes past 3 stations. And because many travel routes may go past the same set of stations in the same order, so we can collapse the travel route into a search route. And a search route is defined as an order set of stations. And this shows you an example of the distribution of search route. So for example, 2,500 drivers drive past station 1 first, station 4 second, station 2 third, right? And we also record the side of the street a station is on, so we can incorporate a left turn cost for difficult left turns when stations is on opposite side of the street. All right, so this table summarizes the station characteristics. So the first row, we can see that stations price a little bit different from each other. So station at the 75th percentile is 10 cents higher than the station at the 25th percentile. And we see a considerable amount of heterogeneity in the quantity transacted across stations. So the station at the 75th percentile is actually more than 6 times larger than the station at the 25th percentile. And in the model, we also control for the brand of the station, the scale of the station, and we also incorporate a left turn cost for difficult left turns. And we see that 12,000 drivers drive past an average station on average day. So that's this number here. And we also find that there's a positive relationship between a station's traffic volume and a station sales volume. And 10% increase in traffic volume correspond to a 12.6% increase in station sales. So this further confirms the advantage of using traffic data. And an average driver sees 3.5 prices along travel route. So we assume that station drivers can see prices from both sides of the street. So this shows that consumers on average have plenty of options along their travel route. And this figure shows that 30% of the stations change its price from the previous day. So prices change very frequently in this market. And we can isolate different sources that contribute to these price changes using this fixed effect regression. So here we regress price on station fixed effect, day of sample fixed effect, and we have this price residual here. So psi j here measures the persistent price differences across stations. So we use this as a measure of a station's price reputation. So this is constant over time. We'll assume that consumers know this prior to search. So before they search, they know along the route which stations are likely are high price station and which station are low price station. All right, gamma T is the price change common to all of the stations. These are likely a result of common cost shock. And nu JT is the price change that is specific to a station on a day. So it is this nu JT that changes the station's prices relative to each other. And studies have shown that it is this the magnitude of these relative price changes is large enough to change the station's price rankings significantly over time, meaning that a low price station will have a higher price than a high price station for a non-trivial amount of time. All right, so gamma T and nu JT here together form we call time variant prices. So they together change a station's price from day to day. So now if I observe a high price at a station, I don't know if that high price is specific to that station or it is common to all of the stations in the market. So that's why upon observing this noisy signal, I update my beliefs about this time variant prices. Right, and this table here summarizes the magnitude of the price uncertainty in this market. So the standard deviation of time variant prices is 3.2 cents per gallon. And the average absolute price level changes from day to day is about 0.8 cents per gallon. All right, so this table shows you some descriptive evidence on price distribution uncertainty. So when consumers do not know about the price distribution, they formulate their prior beliefs based on past prices. So then when, past prices are low, so then I expect prior prices to be lower than they actually are. So that I would search more or even postpone my purchase to a future trip in search for lower prices. So this results in lower sales on my current trip, right? So here we see that past price level can affect current sales through my prior beliefs. So here I regress the quantities at the station on its own price, the price, its neighbor's price, and the price level 7 days ago. I use this as a measure of the prices my consumers observed during their last gasoline purchase. Right, we see that this coefficient here is positive and significant. So this is consistent with the idea that consumers do not know about the price distribution. In contrast, if they know about the price distribution, past price level should not affect current purchase decisions. Right, so for the sake of time, I'm going to skip one robustness result. And let's go to the model. But so far, any questions? All right, so the model. All right, so we'll assume that consumers' indirect utility for 1 unit of gasoline purchase, which is assumed to be 10 gallons, at a station J on day T is equal to the following. So XJ is station J's non-price characteristics. So this include a station's brand dummies and the station's scale dummies. So here we don't include station fixed effect here because we only observe quantities for a subset of stations, and we cannot identify station fixed effect for the stations that we don't observe quantity data. So here we just use brand dummies and scale dummies to predict station fixed effect. And PJ is the unit price of gasoline. So from the price regression, we can decompose the prices into two parts: price reputation and time variant prices, right? So, and based on what consumers are likely know, based on what is likely known to consumers prior to search, we can further divide the utilities into two parts. The first part includes the station characteristic and the station's price reputation. Because this is constant over time, we assume this is known to consumers prior to search. So then consumers search to realize this time variant prices, and they base and update their beliefs about the distribution of time variant prices. All right, we assume that time variant prices follow a normal distribution, and we assume that consumers are certain about the price level, but they know the price dispersion in the market. And recall that the sigma here equals to 3.2 cents per gallon. And consumers hold prior beliefs about the average price level and assume that consumers' prior beliefs are normal. And mu zero is the prior mean, and sigma squared over alpha zero is the prior uncertainty, and alpha zero is the prior weight. So after observing prices, the consumer's posterior mean posterior belief follows a normal distribution, and mu n is the posterior mean, and it is a weighted average of the prior mean and the newly observed prices. And the posterior uncertainty, we can see it decreases when consumers observe more prices. All right, so we see that posterior mean depends on prior mean and prior weight. So then here, note that consumers' prior mean may not equal to the actual price level in the market. And then alpha, which is the prior weight, determines the speed of learning. So the larger the alpha, the slower the update, because now consumers' posterior mean depends more on their prior mean. So a slow update means in the retail gasoline market is that consumers believe that the observed price change is more likely to be specific to that station. So I won't adjust my price beliefs for the other stations, right? And when alpha equals to infinite, then consumers do not learn. And posterior mean equals to prior mean. So the smaller the prior weight, the faster the update. And the faster update means in the gasoline market is that consumers believe that the observed price change is more likely to be common to all of the stations in the market. All right, so order search. So here we assume that consumers are forward-looking. On day T, consumers are assigned a search route based on the empirical distribution of search routes. So consumers each search and learn along their search route. Search here is ordered with no recall, meaning that consumers are not allowed to go back to the previously visited stations. And consumers sampling prices are known. A search route is assumed to be free because they're not making any deviation from the search route. And at the end of the route, consumers are now to postpone their purchase to a future trip. However, they have to pay a postponement cost. And this postponement cost is consumer specific. And so for consumers who have plenty of gas remaining in their gas tank, they have zero postponement cost and they can search forever. And if they are low on gas, then their search postponement cost is going to be high. Right? And then consumers decide at which station to purchase gas by comparing the realized utility at that station with the continuation value of search. Right? So because we introduce a turn cost, so tau here, so then the ex ante non-mean utility is going to be route specific. So then this is a known search route R. So at any station N prior to the final station, the value function after observing the prices at station N equals to the maximum of the realized utility at station N and the continuation value of search. So the continuation value of search depends on consumers' posterior beliefs. And H here is just a transition function of posterior mean. Right, and at the final station, N, so the value function equals to the maximum of the realized utility at the final station and the value of postponement. So because in postponement, so drivers regularly, or consumers regularly drive on different driving trips, right? For example, go to work, go to a movie to see a movie, and go shopping, for example, and then they regularly face different sets of stations. So in order to, and in the data, I only observe aggregated data. So we cannot track individual driving behaviors over time. So in order to take into account these multiple potential search routes, so here I assume that in postponement, a search consumers search randomly draw a search out from the empirical distribution of search route, and then they start their search over again. So then the value of postponement equals to postponement cost plus a weighted sum of the value function at the beginning of each search route. And we show in the paper that the continuation value of search actually is linear additive in posterior mean. So here we can rewrite the continuation value of search as an unknown function z of c conditional on the model parameters and minus the posterior mean. Right? And then we can numerically solve for the unknown function z of c conditional on the model parameters for all of the stations along all of the routes using policy function iteration. All right, so how do we calculate purchase probability? Right, so here in the model, consumers purchase at different stations along a route because they have heterogeneous postponement costs. Right, so if they have a very high postponement cost, they're more likely to purchase at earlier station out of caution. Right, so and also the z of c is actually decreasing in postponement cost. So then at every station, I can find a critical postponement cost that makes this consumer indifferent from purchasing at this station or continue searching. Right, so then I can find a postponement cost lower bound. So for consumers with postponement cost that higher than this critical postponement cost, then they are going to purchase at this station. Right, however, the consumer's postponement cost should not be too high, that they have already purchased from an earlier station out of caution, right? So this gives me an upper bound of postponement cost, right? So for consumers to purchase at station N, his postponement cost needs to be lower than the critical postponement cost, the minimum of the critical postponement cost at the previous stations. All right, and also in the market, most of the drivers driving on the road, they have plenty of gas in the tank, so they are not actively searching for gas. So for these consumers, I assume they have a postponement cost of 0. So here the postponement cost distribution has a probability mass at 0. And then the positive postponement costs follow a log normal distribution, and the purchase probability basically is the probability that postponement costs fall between these postponement cost bounds. All right, so how do we estimate the model? So here we only observe aggregated data, so we don't track individual like purchase decision or driving decision over time. So in order to use this aggregated data, we have to make this estimation assumption. So assume that purchases on each day are made by a new group of drivers. Right, so this new group of drivers arrive in the market with a common prior, and the prior is equal to a weighted sum of the price level 7 days ago and the current price level, and pi is the weight consumers place on past prices. Right, so here we estimate the weight on past prices pi and also the prior weight alpha, and this allows us to empirically test different search models. So when pi equals to 0, so consumers have a correct prior belief. So prior mean equals to the actual price level. So if pi equals to 1, and then alpha equals to infinite, so consumers do not search, but they have a biased prior belief. So this nets the reference price search model in Lewis 2011's paper. And when pi equals to 0 and alpha equals to infinite, so consumers have correct belief and they do not learn. So this nets the standard search model with a norm price distribution. All right, so the estimation procedure is as follows. So it follows 2 steps. So first step, we use the price regression to separate prices into station, price reputation and time variant prices. And based on these prices, and also based on the parameter values, I can solve for Z of C, right? And then at each station, I can solve for the critical postponement cost. And then from that, I can calculate the purchase probability. And then I sum up the purchase probability at a station over all of the routes it is on to obtain the model predicted market share. And we estimate the model parameters by minimizing the square distance between the model predicted and observed market shares. All right. All right, results. All right, so this table summarizes the estimation result. The first column here shows you the result of the baseline learning model. And the second column here shows you the result from a restricted no learning model. So in this model, we restrict prior weight to infinite. So in practice, we set prior weight to a very large number, so consumers do not learn. So immediately we can see that when learning is not allowed, the prior bias is not identified, and also as expected. So the restricted model fit the data worse, as suggested by the pseudo R-square. All right, and now let's take a closer look at the parameters that govern consumers' prior beliefs. All right, so we see that consumers place a 60% weight on past prices when formulating their prior beliefs. So this suggests that the average price difference between the estimated prior mean and the actual price level is 2.7 cents per gallon. And this is approximately 3.3 times the size of the absolute day-to-day price level changes. All right, and we find a small prior weight equals to 0.3, and this suggests a very fast learning. All right, so one new price observation can reduce the initial difference by 77%. And actually, this fast learning is consistent with the characteristics of the market because we see that price levels changes significantly in response to volatile wholesale costs. So then the newly observed prices tell consumer more about today's price level than the past prices. And in fact, if we calculate the magnitude of the estimated prior uncertainty, and we find that to be very similar to the short run variation in price levels. This means that consumers, on average, they make their purchase decisions as if they have a very decent understanding of the volatility of price levels in the market. Right? So here we see on average, consumers are actually doing pretty well. Right? And we also estimate the median postponement cost to be 56 cents for 10 gallons of gasoline purchase. And we find that ignore learning overestimates the median postponement cost by 33%. So how am I doing with time? I have 10 minutes. 10 minutes. All right. Okay. Hurry up. All right. So this table basically shows you that our model can generate very sensible own price elasticities. So the average, recall that we separate prices into price reputation and time variant prices. And price reputation is known prior to search. So an average station's own price elasticity with respect to change in the time variant price is -8. And an average station's own price elasticity with respect to a change in the price reputation is -24. And these elasticities are comparable with what's found in the literature. All right, so this table basically, I regress the cross price elasticity between station pairs on the common traffic shared between the station pairs. And here we see that as stations share more traffic, they compete more closely with each other, and they have higher cross-price elasticities as expected. All right, so this is what's interesting. Here, the model can generate a non-trivial amount of station pairs that have negative cross-price elasticities. And this result is only specific to the learning model. The non-learning model, so in the non-learning model, all of the station pairs have non-negative cross-price elasticities. So in fact, 17%, in the learning model, 17% of the station pairs have negative cross-price elasticities. And why that is the case? So we illustrate using this simple example of 3 stations, right? For simplicity, we consider, let's say, all 3 stations have a positive market share. So then the critical postponement cost at the first station is larger than C star 2 and it's larger than C star 3. So here, this shows the predicted market share at each station, and C star here basically solve the following equations. Right, so let's suppose there's a price increase at the first station, right? So if there's no learning, where alpha 0 is equal to infinite, so then these terms here drop out. So x1 can only increase C star 1 here in the model. So basically here, the marginal consumers between 1 and 2 now choose to substitute away from 1 and purchase from 2, right? So quantity at 1, market share at station 1 goes down and market share at station 2 goes up, right? However, when there is learning, so alpha 0 would be a small number. So then x1 can also decrease C star 2 and can also decrease C star 3. So what does this mean? It means that when consumers observe a high price at the first station, they adjust their price beliefs upward, believing that all of the prices are high today. So they are going to search less and they're more likely to purchase from an early station, right? So then the marginal consumer between station 2 and 3, denoted by C2 star, C star 2. So now they are going to purchase from station 2 and move away from station 3. So here learning can additionally increase station 2's market share, right? So, and here we see that station 2 is station 1's immediate competitors, right? So here we can see that with learning, the effect of station 1's price on its immediate competitor is always positive. However, the effect on station 3, which is a distant competitor, is unclear, right? Because now some marginal consumers so now station 3 loses some consumers to station 2. However, it gains some consumers from postponement, right? So if station 3 loses more consumer than it gains, so then station 1's price would have a negative effect on station 3's residual demand, right? So this can generate negative cross-price elasticities, right? And in fact, we see that negative cross-price elasticities can arise when stations are not immediate competitors. And in the model, on average, so these negative cross-price elasticity station pairs, on average, 3.7 stations away from each other. All right, so in the model, we know that, so here we want to see how fluctuations in consumers' price beliefs affect consumer search behaviors and also demand elasticities. So here in the model, sharper increases or decreases in price level can cause prior beliefs to be more different from the actual prices, right? Potentially leading to larger asymmetry in search behaviors and demand elasticities. And here we construct 2 measures of search intensity: the share of searching consumers who buy and not postponing. So this is column 1 here. And the second measure is the number of stations consumers searched, conditional on purchase. So here we regress these 2 measures on the difference the change in the price level from 7 days ago. And first column, we see that when prices are increasing, more next consumers choose to buy from the current trip and choose to postpone. So this is consistent with the price patterns I showed you earlier. And conditional on purchase, so if past price level is the same as the current price level, so then consumers would search 2.6 stations before they purchase. So if prices today are 10 cents higher than prices 7 days ago, then consumers would search an additional 0.2 stations on average. Right, so they search more, and this is consistent with and also this asymmetric search behavior can result in fluctuations in own price elasticities. And here in the last column here, we regress the estimated own price elasticities at every station on every day on the difference in the price level. And we see that when price level increased by 10 cents, demand becomes 10% more elastic. All right, so essentially this coefficient here tells you how the degree of demand asymmetry when prices are going up and when prices are going down. So in this counterfactual analysis, we want to see how this asymmetric in demand elasticity respond to changes in parameters that govern consumers' prior belief, i.e. prior bias and prior weight. All right, so in this figure here, we hold the model parameters at their estimated value, and we only change the weight consumers place on past prices when they formulate their prior. So 0 means that they have a correct belief, and 1 means that they put 100% weight on past prices. And we see that, as prior gets more biased towards past prices, demand asymmetric increases. So the blue line here plus the demand asymmetry, the further away is from 0, the more asymmetric it is. All right, and in the second graph here, we hold prior bias at 0.6, right? So consumers start with a bias prior, and then we vary the speed of learning. So consumers, we move from a very fast learning to a very slow learning. And we can see that as learning is slowed down, demand becomes more asymmetric, given that consumers' prior is biased. All right, just to conclude, we estimate a model of optimal search by consumers who are uncertain about the price distribution, and we leverage traffic data to simulate search routes. And this order search allows us to identify the learning process in a consumer search framework using only aggregated data. And we show that learning is an important component of price search in this market. And we establish an important relationship between the learning primitives and the search and demand asymmetry. All right, and that's it from me. Thank you.
We have time for questions.
Yeah.
You are assuming someone was after they say, okay, I'll wait till tomorrow to do yes. Something like that. Is that the idea?
Yeah, so they are not purchasing on the current driving trip.
Okay.
So it's kind of like an outside option. They choose the outside option.
Yeah. Another way to think about it could be, okay, I'm just gonna turn around, go to gas, I see the price good, that the station for me.
Right.
And so I'm just curious, how you make that decision to model the postponed cost rate.
Right. So usually, okay, so maybe going to work, they go to work in the morning and go back home in the afternoon. So here the assumption would be that consumers normally, stations change prices during the day. So on the way back, prices would change.
But then when you come back, or when the next day, price can change
Oh, right. So I actually forgot to mention like the prior mean tomorrow. So in postponement, prior mean tomorrow equals to the posterior mean at the end of the route. However, they start with a diffused prior. So uncertainty reset. But so my best estimate of tomorrow's price level is my belief about the prices today. Yeah. So here. Well, anyway, yeah, that's what I just said. Yeah. Yeah.
I have a question.
Yeah.
Would you be able to use your model to analyze the counterfactual in which, for example, the brands like Exxon, Sunoco, whoever, managed to restrict the amount of land that was used for gas stations so that there would be fewer gas stations, less learning, and maybe,
I see.
you see where I'm going?
Yes.
that-
Yeah, that's an interesting counterfactual. Yeah, but yeah. Yeah, we can think more about that. Yeah, that's a good one. Yeah. Counterfactual. Yeah, so fewer stations or even more stations.
Fewer
Yeah.
stations and obviously higher.
Oh, yeah, yeah. Yeah.
I mean, the implication for that is that the number of gas stations in the United States has dropped by a third in the last 10 or 15 years.
Right.
So, I mean, you could just do it relatively simply. Increase fuel economies, reduce the number of gas stations.
Right. Yeah. Yeah. Good idea. Thanks.
An alternative simulated that obviously is an app that would give you prices on your route. Right, there are some countries which mandate reporting of various prices, and with the hope that it'll be aggregated and put on.
Right.
I think in the US, we could prove it, you know, and you get the like, you know, along the way, or the focus.
Somebody in the room knows that the biggest conclusion to that.
Yeah. Right. Oh, so by the way, so the data we use, so the sample is in 2016. So the adoption rate of online search platform is like 20% from memory. So it's no, everyone is using it, but in counterfactual, yeah, I see. Yeah.
Phasing updating of the price.
Mhm.
Being as a three parameters.
What should,
You never still have to reset, that's changing the common game.
Yeah.
reset is at the end of a route. So yeah,
Beginning of the next route, that's.
Yeah.
the current common game.
So there would be an optimal amount of data. The features of the 3 months or.
not sure I'm following, with,
depending on whatever's there.
right, so you are saying there's an optimal learning rate?
Yeah.
Oh, okay, right, so, okay, yeah, so
How does it?
actually, so yeah, so that result shows that consumers are essentially learning quite optimally. Right, so it actually, so the prior uncertainty is actually similar with the variation in price levels. Right, so here in the model, we are not imposing that consumers are learning optimally, but from their purchase decisions, we back out their learning rate and we find that they are actually learning quite optimally.
You're not imposing it.
Right, we are not imposing, yeah. Yes. Yeah. So they may be, so if they do not know like the price level variation, right? So they may learn too slow or they may learn too fast, right? And that results in different purchase decisions. And we find that they are actually, yeah, that's an interesting result. Yeah, that's yeah, this here. Yeah.
Okay, you know, that interesting result.
Yep. Wow. Thanks.